It's my pleasure to introduce my colleague Mikhail Belolipetsky from IMPA, who will talk about growth of k-dimensional systoles in congruence coverings. Thank you.
Thank you very much, Vinicius. I would like to thank the organizers for the opportunity to speak at this very interesting meeting. So it's about systoles and diasystoles. But looks like everybody is, most of the talks are about different subjects, and my talk will be about different subjects, most likely. But I hope you find it interesting. So to begin with, I need to define, we have systoles and diasystoles. Now they will be k-systoles. So that definition probably is familiar to people here, but still let me remind it. So an absolute k-dimensional systole of a Riemannian manifold M. So M will be always a manifold with Riemannian metric, is defined as an infimum of k-volumes of subsets of M, which cannot be homotoped into k-1 dimensional subset. So which can't be homotoped to smaller dimensional subsets. Here we assume that k is less or equal than dimension of M, which will be n usually. And this is definition due to Gromov, which is a natural generalization of the one systole, homotopy systole, the length of closed geodesic loop, in smallest length of closed geodesic loop. And here we are talking about k-dimensional cycles. And there is also a definition which is in fact preceding one of homological systole. Which is which depends on coefficients A that can be usually either Z or Q or Z2 or ZP, etc. But these are the most common. So these are infimum of the K of the volumes of non-trivial k-dimensional cycles. So infimum of volumes of cycles not zero in homology with coefficients in A. Case homology in coefficients is A. And okay, this was a Gromov that is by Marcel Berger much earlier. And more recently, these homological systoles find some applications in computer science. That's why they there is one other reasons why they consider to be interesting. So what we would like to do is to study these systoles in expanding families of manifolds.
Why the first absolute?
It's just to distinguish it from homological. This is called systole, so without any word. And that, okay, Gromov called it absolute systole. It doesn't depend on coefficients yet. It's only homotopical object, so more topological in a sense, yeah. So we are interested in these systoles in expanding families. Families of manifolds. So what can it be, this expanding family that requires some more definitions? I will go very quickly, but okay. You take some, say, semi-simple Lie group. And it's, okay, symmetric space. So for instance, you can think about SLN R, okay, SLN C, or SO MN, orthogonal group of signature MN. I want it to be non-compact. And this is the quotient by maximal compact subgroup. So, well, if you take, for instance, here SON1, then it will be hyperbolic n space, and etc. You get various symmetric spaces. And we look at the arithmetic quotient of this. So gamma is so-called arithmetic subgroup. And the simplex example here will be group of integral n by n matrices, or, group of, again, of so-called units of this quadratic form. There are many other arithmetic subgroups. In particular, there exist co-compact and non-co-compact arithmetic subgroups, torsion-free, etc. And okay, this will be the base, and then we look at the coverings of these defined by so-called congruence subgroups of gamma. So congruence subgroup, which again in this basic example will be just group of matrices so this is, I reduced to one example here, a group of matrices, say A, which are equal to 1 modulo P. So these are, and this is finite index subgroup, which moreover is torsion-free, and we have a sequence, or we can just take here powers of primes, then we have a tower of congruence subgroups. So upshot of this, that we have an explicit construction, in fact, many sequences of Riemannian manifolds. And there is something very special about these sequences. So one of the main properties which is important for us is that they are so-called expanders. So the congruence subgroups or the congruence coverings have the property that their spectral, the first eigenvalue of Laplacian on these covering spaces, Mi, is uniformly bounded by positive constant, which depends on x, but doesn't depend on gamma or the index, so it's uniformly bounded by a constant. And also, this, in general, this kind of results, they follow from representation theory. But they have a geometric application. So as a corollary, we have that the Chigger constant of Mi is also uniformly bounded by some other constant, C1, C2. And that is a corollary of Chigger's definition of his constant and Boozer-Chigger inequalities, which relate spectral gap of Laplacian and the isoperimetric Chigger constant. So I expect that isoperimetric constant is familiar. Inequality. And this is how it works. And when we have some sequence of manifolds which have this property, because they have this isoperimetric, Sorolla isoperimetric property, it's very hard to cut them. In order to cut them into two halves, you need to really cover the area proportional to the volume. That is called expander in graph theory or in geometry. So this makes Mi geometric expanders. And here we are talking about hypersurface which cuts this space into two, say, equal halves. But apparently the geometry of these spaces is interesting. And one of the reasons to be interested in k-systoles of these spaces is to understand more about their geometry. So here we only have hypersurface, but what about, say, two-dimensional surfaces, maybe minimal surfaces or totally geodesic surfaces? Well, a priori, you don't know what will come out when we look at the area minimizer, but there are obvious candidates. So to conclude with this introduction, I should say that you can just start with these properties and study geometry of the spaces which have this expansion property. The reason to introduce all this, and actually more that I didn't mention, is that this part gives explicit construction of these spaces. It's so explicit that you actually can put it in computer and do experiments. And also, when you prove some theorem, you can give it to computer scientists and say that, there are these matrices which apparently we discovered they have this property, and sometimes they find it useful. So that's one of the reasons. And also, this is about construction, but the construction comes with the bonus that you have a lot of tools to study these spaces, starting from geometry, but also there are some prime numbers here, so there is number theory that allows you to work with them. And that makes them attractive. Eventually, if you prove some results about geometry, say, of this particular class of expanders, you might try and succeed in generalize it into wider setting. So that's how it works. Examples I already mentioned to some extent. I want to introduce the rank. Yeah. To state the result, I want to state theorem and then discuss it. I need one more definition of so-called real rank of manifold, of locally symmetric manifold. So the real rank R of M, which is actually defined as a real rank of the big universal cover of the symmetric space, is the dimension of the maximal connected flat subspace. Flat means zero curvature of X. So is the maximum dimension of connected flat Euclidean totally geodesic subspace in X. And okay, let me finally state the theorem, but then I will say more things about rank. For instance, okay, in SLN R, the rank will be equal n minus 1. So it can be as large as we want. In hyperbolic, well, so in SO, Mn, the rank is equal to the minimum of these indices. So in real hyperbolic spaces, the rank is 1. But if you take SO, say 2M, quite popular group as well, then the rank is 2. And we are, so why I'm talking about this rank, that we are interested in so-called higher rank, so when it's bigger than 1. So SLNR is a good case for us. The theorem which I would like to discuss is the following. So it's a joint work with Weinberger, and it finally appeared last year. But so the theorem is published and proved, but then there are things which we are still working on, and I will try to comment on that too. So M is compact arithmetic locally symmetric space. MI congruence covariance. And what else? I assume that this real rank of M or MI is fixed, equal to R. And I need one more constant parameter, which is so-called strongly orthogonal rank. I will define it in a moment, but let's first see what we can say about this. So we have the following inequalities for systoles of the congruence coverings. There will be three modes or three ranges. One when the dimension of the systole is smaller than or equal than strongly orthogonal rank. Then something between rank and strongly orthogonal rank, and then the rest. And so I don't have much time to explain, but there is some history about these inequalities. So some of them are due to Gromov, and some of them were announced by Gromov, but okay, were not without proofs. And some of them do not appear in Gromov's notes. So, well, so in the first regime, we have logarithmic power of logarithm upper and lower bound for this absolute systole. And this is when the dimension, okay, it cannot be 0. It's between 1 and R1. Okay. And then the second option is when we can prove that the lower bound is active volume for the absolute systole is logarithmic in volume, and upper bound is power. Some volume mi to power gamma, where gamma is actually, here it's always strictly smaller than 1. So there is some power which is smaller than linear. And here we have this intermediate range. So R1 is smaller than K, less or equal than rank. And the third possibility is when we are above the real rank. And here we have power bounds. So beta K. And here we can only say that gamma K is less or equal than 1. Well, here is also gamma K. Yeah. And K is now between rank and the dimension of the manifold. Well, let me continue a little bit on this side so we can prove a little bit more. In particular, in the third inequality, here, when M has a totally geodesic subspace of dimension K, has immersed totally geodesic subspace of dimension K, K subspace, then this gamma K is strictly less than 1. So it applies to here as well, but here, by definition of the rank, we do have totally geodesic tori. So that's why here gamma k is smaller than 1, and it's actually equal to, maybe I should write, it's bounded above by 1/3. So it's much slower than linear. But here, it may not contain any totally geodesic subspaces in, say, of codimension 1. There are examples, so you know that. So a priori, this upsystole can grow linearly with the, say, upsystole of dimension n-1 can grow linearly with the volume, potentially. So in the paper we left it as an open question, and recently the first example of such linear growth appeared in a very interesting paper by Mikhail Belolipetsky and Ben Lowe. I hope I will say more about that later on. Wait, so this I stated, and I should say something about homological systole. So if we have that homology of Mi with coefficients, okay, it depends on coefficients, with coefficients in A is non-zero, then by definition, basically, we always have that homology systole is bigger or equal than absolute systole. So we have upper bound. And this is, in a sense, the main source of the bounds for homological systoles. So when we can prove something about this absolute systole and somehow detect that the homology is non-trivial, we automatically get the one-side bounds, so this all kind of part applies. And then if we know something about the cycles that are non-trivial, and okay, they are duals and a product way, we can often say more and also give some upper bounds. I may not be able to say much more today about this homology systole. In order to conclude with the statement, I need to define this strongly orthogonal rank. This kind of new, well, in a sense, it's not new because it appeared in representation theory for split groups in Harishchandra's work, but okay, we can generalize it a little bit, and in geometry it didn't appear before. So well, the definition is roughly that if you have, so it's roughly speaking the maximal number of positive roots in root system of this symmetry group of H, which are mutually orthogonal with respect to Killing form. So there is a natural product on the root system of H induced by Killing form, and so these roots are So this may look a little bit confusing. The idea is very simple. For SLN, it's easy to explain, and I will explain that. So for each root, in the root system, you have a map homomorphism from SL2R, 2 by 2 matrices, to your Lie group. And say, look at this SLNR now. So what is this? Is just n by n matrices with real entries. Then there is a root system, and for roots you associate these blocks, 2 by 2 blocks of matrices. Can be also like somehow spread like this. This, like say, another 2 by 2 block. And okay, there are various ways to put it inside copies of SL2 inside SLN, but you can notice that if n is big enough, then you can always put some number of copies of SL2 that they don't overlap. So meaning that the corresponding group elements commute. And that is the idea, that the maximum number of mutually commuting SL2s you can put in your SLN is that strongly orthogonal rank. So that geometrically it means that you can choose cycles in each of these subgroups totally independent, and they will commute. And then if you have a commuting non-trivial cycles, there is actually a beautiful theorem by Gromov and whose theorem is this? Gromov and Wolf, that tells you that you can always span a flat torus on commuting cycles. So this is like intuitive explanation of strongly orthogonal rank, which also gives you intuitive explanations of this inequality. So let me now just proceed little by little with comments about what we know and what we find interesting about these k-dimensional systoles. I still have some time, so I will not try to get too many details, but I will try to go by each of these inequalities and point out something which I find interesting about each of them. So, like the first inequality, the first step is a well-known fact that systole of mi grows like subconstant log vol mi. So we are talking about compact Riemannian manifolds. That means that systole is twice injectivity radius. Injectivity radius, you can put a ball of radius r in mi, and mi has, so it's not positively, it has some negative curvature because it's a locally symmetric space of semisimple non-compact group. So this negative curvature implies that the volume of the ball will be kind of exponential of this injectivity radius. And this argument implies that absolute systole will be smaller or equal than some constant log of the ball. And interesting fact is that for this congruence covariance, in general for geometric, no. So in general, if you have a regular covariance, which are expanding family, so they have bounded trigger constant, then you can prove that absolute one-dimensional systole behaves like a logarithm of the volume. And there is an interesting question about the constant. So not many. So the constant is known for some cases. In particular, Plinio, who was here yesterday, Plinio Murillo, did interesting work about that. Well, so we know one-dimensional systole. And then if we have dimensions smaller this strongly orthogonal rank, then we can kind of choose this cycle. The definition of strongly orthogonal rank enables us to choose these cycles of about these sides totally independently, and so that they commute. And well, the upshot of this is that this inequality allows us to prove that if dimension is smaller than R1, then log so I like don't write constants. I explained the idea behind this and this, but the proof, well, here it's definition of strongly orthogonal rank and Gromov-Wolf theorem. Here there is one of the, in fact, most astonishing results in this systolic geometry, the Gromov intersystolic inequality. Yeah? So Gromov's systolic inequality for essential polyhedra. So with these two powerful theorems, you can make the hand-waving into a strict argument, and the inequalities follows. And if you are curious about details, I think we did our best to write that in the paper. Well, what happens with when the dimension becomes bigger than R1? So K is bigger, strictly bigger than R1, and still less than R. Well, we still have tori by definition of the rank. And the logic here is the following. We are looking for smallest area non-trivial cycles. So if there are some flat subspaces, then they will be the most natural candidates, because if it's not flat, the injectivity radius is always bounded by this. So if it has some negative curvature, then its area will blow up. So naturally, if we have flats, this will be, and they're homotopy non-trivial, then this will be our candidates for systoles. Well, and here we do have flats, so still have flat tori. But now we cannot choose their parameters totally in a totally independent way because, for instance, maybe let's have an example. So the basic example is when the group is SL3 R, then rank is equal to 2, so it's high rank already. And the strongly orthogonal rank is equal to 1. Just think about 3 by 3 matrices with determinant 1. Then you can put, of course, a copy of SL2 inside here, but you cannot put 2 copies because they will overlap, and that means that the images will not commute. Okay, they are not independent. So the second doesn't fit. Maximum you can do is 1. Easy exercise. So, well, but what it means for torus, for tori that appear here, is that when you choose, so you want to choose meridian and parallel very short. But when you choose one of them very short, it kind of forces the other one, because the torus is totally geodesic immersed, it forces the other one to become very long. So it's not like you just put 2 and the log square come outside the area. You make one of them of the length log square, and the other one becomes is forced to be proportional to the volume, much longer. So that is the issue, and it actually knows how much I will say about that, but it actually can be observed, like geometrically or numerically for many tori. Like, statistically, for most of the tories can be observed. When you when meridian is short, it forces parallel to be long, and vice versa. This is the phenomenon which appears here, and it appears also in other fields. So, well, and that is why we made many experiments, and we noticed that what happens in this intermediate range is that the volumes of the tori tend to oscillate between logarithmic and power bounds, sticking with most of the tori, like with probability 1, sticking close to the upper bound. Eventually, we discovered with Altan Erdigor, who was a student here, we discovered more about this phenomenon, and the part which is more is currently work in progress, which I hope we will be able to present soon. So let me perhaps not tell more about this intermediate range. I think it's very interesting. And so upshot is that now for this basic case of SL3 and SLZ, in SL3 we know more than I presented here, and even more than, and also more than we wrote in the paper, but only about absolute systole. And homological systole, there is total mystery, the behavior in this. So basically, you want to find two-dimensional short cycles in these locally symmetric spaces here. The dimension of the space is going to be 5. Yeah, because, okay, the space is SL3 by SO3, and if you count the dimensions, you check that it has dimension 5. So, well, one-dimensional system we understand well. Then there is 2, which fits into this rank, and we know something about absolute. We don't know nothing about homological with whatever coefficients in this case. But it's possible to even put it in the computer. It's just 3 by 3 matrices. And to, say, run till primes up to 100, and you start to get pictures. Very entertaining example. And then, okay, then we still have, dimension 3, 4, and 5. So let me tell about the last 10 minutes. I'm going to talk about this third inequality. In order to third inequality, I need to erase something. So in third case, the dimension is already bigger than dimension of any totally geodesic flat subspace that is contained in our manifolds. So, well, K bigger than R. The first observation is that there are no K flats, meaning that you look for this area minimizer somewhere else, not flat. Also, it indicates that we have some amount of negative curvature. And if one manages to capture this negative curvature, then one expects to get bound like this. Well, why? Because, so let me just say some observations. Negative curvature, injectivity radius about log volume. So let's say k-dimensional negative curvature. Injectivity radius log volume. These together should imply that k volume of the cycle, of incompressible cycle, is bounded below by something like exponential to injectivity radius, which is going to give you some power of the volume. So this is the idea, and actually it's possible to make it work. How do you make it work? There are three ingredients. Perhaps there is even, I believe it's not the only way to prove it, this bound, but I think our way is efficient, and any other approach would, we encountered technical difficulties, and if you do some other way, you will encounter technical difficulties too. So you will have to find a way to work through them. But so I wrote something here, which is like hand-waving idea of how to prove this inequality. Now the way to make it into into a mathematical argument is to use some known theorems. So known theorems first is that we have linear isoperimetric inequality for filling volume in this range. And that is, well, okay, was announced by Gromov and proved by Robert Young and Enrique Leutzinger. So some people worked on it before, and now we have a complete proof. So of linear isoperimetric inequality for filling volume of the cycles of this dimension. So I'm sorry I'm not giving sufficiently many definitions. You can find them in the paper, but most of people here are familiar with these terms, so I'm trying to indicate the idea. Then, so you have this volume for fillings of the cycles, and it satisfies linear isoperimetric inequality, which is another manifestation of negative curvature. Like in negative curvature, you know, the perimeter of the circle and the area of the circle are connected by linear inequality, linear relation. So, and then we can put this linear isoperimetric inequality into co-area formula. So we already know also injectivity radius. And these ingredients, together with some results from Federer-Fleming deformation theory, allow you to prove this bound. So the proof is, it uses a lot of previous Weinberger's work, so I was lucky to just ask him what to do, but I think it's quite interesting, the proof. 5 minutes, even less than 5 minutes left, and I still want to say a few words about this inequality. So this was about lower bound for apses. So the upper bound. Firstly, you can triangulate. We can triangulate our manifolds Mi. And triangulation, K-skeleton of triangulation will be an essential. Is essential, implies that the area of K-skeleton gives the upper bound for the K-dimensional absolute systole. So it's an easy path, K-skeleton and it works in all dimensions. So in any dimension you have this bound. Quite surprisingly, in some dimensions, this bound can be optimal. So you cannot do any better. And that way, we in the paper, we leave it as an open question. Can this bound be sharp, okay, optimum. And then the result I want like to mention, advertise is by, not by us, is by Ben Low and Mikhail Belolipetsky. Okay, swap the names, but I've learned it from Ben, so who was here in January. So what they prove is that this holds true. So can this bound be optimal? It is for, so the examples are very bizarre. For 16-dimensional octonionic hyperbolic manifolds, compact octonionic hyperbolic manifolds, and the dimension in which they proved that the growth of systole, K-systole is linear, is 14 and 15. So, okay, 16 is not interesting, it's the volume. Codimension 1 and codimension 2 as well, they proved that any totally geodesic, well, no, actually there are no totally geodesic subspaces there in this dimension. If there is totally geodesic subspace, by our result, it implies that this is not possible. So first of all, there are no any totally geodesic subspaces, but any homotopical non-trivial cycle in these dimensions, which will have very large area, well, as large as it can be. So it's they call it they relate it to expansion and call it some strong form of expansion. This very recent, it appeared in December, I think, on Archive. And most likely, this is not the smallest possible dimension where you find this phenomena, but okay, the proof they have works here. So I finished my time. Thank you very much for your patience.